Okay, let's get started. And today is our great pleasure to have Professor James Murphy from Tufts University give us a talk. So James received his PhD at University of Maryland and also had a postdoc at a Duke and Johns Hopkins before joining Tufts. And his research is at the intersection of the harmonic analysis, data science, and applications to image and signal processing. His group is currently focused on unsupervised machine learning, analysis on graphs, optimal transport, and application to hyperspectral imaging and molecular dynamics. So James, please.
Let me switch back. Okay, so everything looks good here?
Yeah.
Okay, great. Yeah, thank you to the organizers for the invitation. It's really nice to be here digitally. I'm looking forward to hopefully next year doing some in person.
Yeah, we'd love to have you here.
Okay, great. So I'm going to talk about kind of a line of work that's kind of at the intersection of harmonic analysis and sort of thinking about operators on graphs and some problems in unsupervised and semi-supervised machine learning and some applications in image processing. So I've been working on these things for about 4 years, and I'm going to go from what I would say are like shallow methods in sort of the current lexicon. So these would be things where, we handcraft certain, certain ways of comparing objects and look at operators on graphs built out of those ways of comparing points and sort of move maybe towards a more deep learning approach where we're going to not quite use deep networks to define the representations, but really use them to solve some hard signal processing problems that we think kind of get at this idea of, how do you make comparisons between points in a way that will kind of find these latent structures in the data without supervision. So the problem I'm going to be focused on is an instance of unsupervised learning, specifically clustering. So this is where you observe some data points, you want to assign labels to them, but you don't have any training data. So you can kind of think of this as like you're trying to find intrinsic structure in the data. It's different than I think the most kind of common instances of machine learning where you have lots and lots of labels of who belongs to what class. Here, the problem is kind of, on the face of it, ill-posed. So we're going to make a stochastic data assumption. So we're going to assume that our observations, x1 through xn, are IID samples from some probability measure. And the way we're going to kind of make this tractable is we're going to impose some rigidity to the kinds of measures we consider. We're going to consider mixture models. So the probability measures mu we look at are linear mixtures of some, you could think of them as like atomic measures, mu k. These are corresponding to like the clusters. I have some weights associated with like how often I sample each one, and maybe I have some background noise mu tilde. It's just an illustration in the upper right here. Would be like k equals 4 here, right? You have these 4 elongated sets that I'm sampling basically uniformly from, and then I have some background noise. So the problems that we're going to be interested in it's sort of like a labeling problem, right? So, given these observations, and let's say I know the number of clusters k, can I sort of make assignments of who belongs to the same cluster? Just like an accuracy problem. So we're going to be interested in designing algorithms where I can bound this accuracy from below with high probability, or maybe give instances where I can get perfect accuracy with high probability. And then there's sort of like this lurking model selection problem, which is, can I impose some structure on these measures that's flexible, right? I don't want to be too rigid, but in which I can still potentially estimate the number of mixture components k, the number of clusters, if you like. So we're going to focus on methods where we can try to get a handle on both of these things, theoretically, and try to have it also work on some toy real data sets at least. So this is a well-studied problem. What do people do? I think the most standard thing would be if you talk to like your undergraduates in computer science, they would run like k-means on this probably as a first step. So the idea here is I'm going to cluster by taking in as an input a number of clusters k, and essentially doing like an expectation maximization routine where I iteratively partition points. I compute centers or average elements of each partition, and then I assign points to their nearest centroid, and that gives me new cluster assignments, and so I re-update the centroids. And that's essentially what people do to solve this, right? It gives you an iterative algorithm for solving or attempting to solve the following non-convex optimization problem, which is written at the bottom. So we're trying to find partitions so that when I think about each point being assigned to a partition, I look at the centroid of that partition. I want to minimize the distance between point in a cluster and its centroid over all possible points and partitions. Now I'm going to talk about the optimization challenges of any of these problems. It is a topic of research. I just want to argue that this is maybe not a smart thing to do. Right, it does work well on these examples. I'm showing you in red the centroids and the colors that come out of it. I mean, this I just ran in MATLAB. Didn't really think too hard about the optimization properties of this, but it's really easy to come up with examples where this doesn't work at all. And it's because there's kind of like a latent data model, like a latent generative model that this is designed for, really, right? That you sort of need to have data clusters that are like, you can draw like circles around and not have the circles you draw intersect with each other. That's like when you can do this well in principle. And it's really easy to see those examples, but this doesn't work. So we didn't, notice this, right? This is an image more or less from a famous NIPS paper back when it was called NIPS from 2000 by Michael Jordan and Year Weiss and Andrew Ng. And so their approach was to say, well, what we're missing here is the notion that like nearby points in the data are probably going to have the same cluster assignments. That's like a useful prior to bring into this problem. So don't just think about like distances, which is what k-means thinks about. Think about like this idea that nearby things should get the same label, right? So thinking about connectivity properties of the data. So the way that they approached, that they proposed to kind of capture that idea efficiently is sort of this language of spectral clustering, right? So you instead of thinking about the raw data points, you represent it as a weighted graph. And the way we will think about doing that is you pick some metric, more on that later, and you build a kernel around that, right? So we're going to define a matrix W, so it's number of data points by number of data points. An entry in that matrix looks like e to the negative, whatever metric you picked squared divided by a scaling parameter sigma squared. So this is going to have large values for at ij indices when xi and xj look similar according to my metric, right? So this will be sort of the first theme of this talk, is like thinking about like handcrafted metrics in this case, and can we prove performance guarantees when I think really hard on what metric to use here. So, one can work with this weight matrix W. I think the kind of more elegant and theoretically appropriate technique is to not use W, but to essentially use it to build like a graph Laplacian or something that's resembling a Laplace operator on the data cloud, and look at the spectrum of that. But just to give you an illustration, if you're unfamiliar, so here is that SMILE data that k-means totally fumbles. Down here, I'm showing you what the weight matrix looks like, right? So you can kind of see I've got 3 blocks corresponding to the 2 eyes and the SMILE. This block here is the SMILE. You can see there's a lot of decay off the diagonal because points on opposite ends of the SMILE are kind of far apart. And then I have these eyes here that are more coherent, if you like. They have smaller diameter. So I build this Laplace operator, I compute a spectrum, and then I'm going to represent my data observations in this, if you like, this sort of new basis, right? The spectral basis coming from this graph Laplacian. In the language of Fourier analysis or harmonic analysis, if you like that perspective, what we're really doing is applying like a unitary transform here, right? We're taking the data, representing it in this eigen basis, and then thresholding that, right? And saying, let's only look at the lowest frequency components of that spectrum. And sort of the whole literature around this, or one aspect of it, is to argue that these lowest frequency eigenfunctions are going to oscillate in the directions that capture the cluster structure. So if you use these eigenfunctions to represent your data, it's going to be easy to sort of run k-means on this, for example, and then have it perform well. So the name of the game here is to say, okay, what can I say about the eigenfunctions? And then are they sort of looking the right way so that when I run k-means on it, it works well? So just to give an illustration, this sort of toy SMILE data set of why it works, what I'm showing you here is the spectral embedding of the data, right? So instead of looking at the original, if you like, XY coordinates, I'm looking at the representation in the first two Fourier modes of this on this graph. And what you're seeing is that smile, which was a problem for k-means because it's very elongated. In particular, it's not. It doesn't resemble like a sort of a spherical thing. It gets really compressed in this representation. And if I run k-means on the embedded data, it works really well. So awesome, like at least in this sort of toy example, empirically it works. So what we're interested in is sort of developing theoretical guarantees on this approach that will, in particular, give me some estimate on the number of clusters and how to pick the other key parameter here, right? So the idea is we're running k-means on like a certain number of eigenfunctions here. So I need a good estimate on the number of clusters in my data. And I need to figure out a good way to pick the scaling parameter sigma for this data. So those are my two key parameters. And I want methods that will either be robust to those choices or ideally give me some kind of feedback about what the kind of correct parameters are for a given sort of latent generative model. So again, we did not propose this sort of method we're going to analyze. But what was observed in sort of the original approaches here is that, well, the eigenvalues of this Laplacian sometimes are helpful, right? This is again like a classical area of applied math, right? Spectral graph theory. The first eigenvalue is always zero, right? Kind of corresponding to the idea that you have this like very low frequency or really constant functions in your eigenspace. And then after that, they're sort of increasing. But what people were observing empirically is that you would see a big gap between eigenvalues corresponding to like the number of clusters in the data in some cases. So if you saw 3 clusters, you would see something in practice was like lambda 1 is always 0, lambda 2 and 3 are close to 0, and then big jump up at lambda 4. So there was a large gap between the third and fourth. And that was sort of suggesting, maybe that looking for where that big gap is could tell you something about the number of clusters. So we'll call this the eigengap heuristic. And we're going to, it works sometimes, not other times, right? It's totally heuristic. So we're interested in modifications and sort of ideas related to this that will let us guarantee that this works well, that we can provably estimate the number of clusters using this eigengap statistic. So the approach that we developed was to, again, kind of reiterate this, to kind of think about handcrafting features here in the language of sort of contemporary machine learning, which was we wanted to find a metric such that for a pretty rich class of data, we could prove that, if I use this metric with spectral clustering, I get good accuracy, and I can be robust to the choice of scaling parameter, right? And I can identify the number of clusters correctly. Otherwise, one could really argue whether it's fair to call these methods unsupervised, right? If you need sort of like, incredible insight about what the parameters are, it just doesn't seem to really fit that theme that you go into this not knowing very much. So to us, this was kind of like, the main name of the game. So the method that we sort of developed was what we were calling the longest like path distance. So it is a graph-based distance. So given all of your data points, you build something like a Euclidean nearest neighbors graph on those, and you define something that's like an L-infinity geodesic on that graph. So you minimize over the space of all possible paths, and the functional on a path that you minimize is the longest edge size in that path. So this is kind of like, if you kind of squint, it looks like almost like a classical shortest path problem, right? You have this outer minimization over all paths, and then instead of minimizing, say, the sum of all the edges, you just take the largest one, right? So at a high level, what this is doing is it's really reshaping the geometry of the data sets so that you pay a lot more attention to directions in which you can take lots and lots of short steps, because those don't cost you really anything here. Computationally, it looks kind of bad at first glance, but if you think about it as like an L-infinity geodesic, that might suggest that actually you could use something like a Dijkstra algorithm or maybe a modification of that to get this pretty fast. And that is true. Okay, so we're not going to talk too much about the computation here, but suffice it to say, this is no worse than computing a classical shortest path algorithm. And in fact, it's better, right? If you're willing to tolerate a tiny bit of error in generating this, if you're willing to do this approximately, This metric has an ultrametric structure to it because you're doing this kind of like mini-max computation, but that is actually very favorable to doing high-quality approximations. So you can get this to sort of interact with the spectral clustering extremely well, but I'm not going to talk too much about that. So we wanted to think about like, okay, what's the generative model here, right? That is more robust than what people already have, right? Like k-means, if you think the generative model for that is basically clusters that are like, roughly circular and well separated. What is it for this? So this is just an illustration of sort of what matters here, right? So here I have these sort of like kind of linear, almost like subspace-like clusters. Some of them are long, some of them are short. There's some separation between them. So this should give an indication of what's good about this metric. So on the left, I'm showing you the Euclidean weight matrix for that data set, right? So got ones on the diagonal here because everything is distance 0 from itself. And then you sort of see these different decay rates off the diagonal, right? So the first and third block here are these like elongated clusters. So you have more rapid decay there because things are farther apart. You have a little bit sort of slower decay on the second and fourth blocks, corresponding to like the stouter clusters. On the right, you see what you get if you use this longest like path distance, and there you have not this matrix isn't quite low rank, okay, but it's like plausibly rank 4, right? I mean, it's roughly rank 4, right? You see these sort of like 4 blocks here, and what this is saying is like each of those clusters is highly coherent, right? All the distances look pretty similar and pretty small within that cluster. And also the distances across clusters are really large, right? They're very close to 0 when I kernelize them. So this is like the dream for spectral clustering, is to end up with like an adjacency matrix or weight matrix that looks like this. Because if I think about the eigenfunctions that are going to come out of this, they're going to be, of course, orthogonal, but they're going to also be more or less supported on disjoint clusters. So it's very easy to prove that like under this kind of, or approximately something like this, the eigenfunctions are going to be very easy to cluster with k-means. And so that was our basic approach. So obviously this is like way too easy, right? Lots of things could do this, right? These clusters are linear. There's like very strong separation between them. So obviously we want to do a little bit more than that. So the basic picture that we could handle.
Sorry, James.
Yeah, Ron, go ahead. Sorry, I can't see if anyone's raising their hand. So go ahead.
Can I ask you a question in terms of previous slides? So this color map is the exponential of that minus distance, right? It's not distance.
Yeah, right.
Okay.
That's right. Yeah. So this is basically just like flipping night and day, right? I could show you the distance,
Sure.
and it would just be an inverted picture.
Yeah,
right?
It's like close to 0 and okay.
Yeah.
Okay.
I mean, so typically, like one would look at actually not even W here. You would look at the Laplacian, but because these are like the clusters are roughly the same size. All these weights within a cluster are basically 1. There's almost no difference between looking at the Laplacian and the weight matrix in this kind of toy example.
I see. Is there any intuition? Say, you choose the max of the distance instead of summation, which is more like a geodesic. Here is, as you mentioned, it's like infinity.
Yeah. So so I'm going to get to kind of a relaxation of this, right? But really this is saying, let me go here. So if I take points in opposite clusters, right, the problem is that there is no path that doesn't have a big step between them, right? So any path has a sort of pays a large price to go between 2 clusters, right? So the point is that this point here on the end, can you see my cursor here? Yeah, okay. So this point here and this point here are like far in Euclidean distance, but every path, there is some path connecting them through this whole data set where like where all the edges are not too big. Okay. So in that sense, because there's like a high density path here, it gets compressed. Going across the clusters, right, there is not a high density path. right? And that's what's really going on here is we're sort of imposing a density penalty on the geodesic path. Okay, so you have to be really, you're going to you're going to be willing to take very long paths with respect to like a classical shortest path distance, with respect to like a geodesic on the manifold sense. You'll be willing to take very long paths that way if they're sitting on high density contours. Is sort of the intuition.
I see. I see.
Does that make any sense?
Yeah, makes sense. But what if, like, in between you have some noise, like you sort of merge this two cluster a little bit? What gonna?
Indeed, right? So there's a certain kind of noise which we're happy with, which is I would say like the kind of typical noise in manifold learning, right? Which would be either you have like something like a little bit of so you take these data points and then for each point you perturb it by like bounded Gaussian noise.
Sure.
Or so not bounded Gaussian noise, but like a Gaussian noise with like not too high a variance or something, right? So you add a little perturbation to each point. We're fine with that. What we can also do is, in some sense, unbounded noise. We can have a lot of background noise as long as it's, say, uniform, right, or not too high density. We
Okay.
do have an adversary, right? Our adversary is high density, concentrated noise, right? So if you think like, these sort of dumbbell pictures that like appear in like a lot of the classical manifold learning papers, like diffusion maps papers or something, where you have like two big clusters, like a bridge connecting them.
Uh-huh.
The point is that those methods, right, are robust to the bridge, right?
Yep.
Because the low frequency eigenfunction still oscillates in the right, kind of where it's positive on one bottle and negative on the other. Here, that totally kills us, right? So that's our adversary.
I see. I see. That makes sense because you totally change the geometry and the geodesic will give you. Okay, that makes sense. Thanks.
Yeah, yeah. So let me. I have more to say about that a little bit later. Yeah. So right. So what's the model for this? I mean, the basic idea is we want our clusters to be somehow intrinsically low dimensional. They don't have to be linear or anything like that. They also, we're not really exploiting any of like the Riemannian structure, right? So, kind of in these manifold learning contexts, you might care a lot about the smoothness of the manifold that you're on. We actually don't. We really just need it to be sort of locally low dimensional. So we have this kind of technical definition here, but it's basically saying that like, okay, our cluster sets need to, when I zoom in enough, look like little d-dimensional Euclidean spaces, right? Maybe there's some kind of like curvature going on, smooth or not smooth, whatever. I count for that with this kappa constant here. So you can think like if you have like a smooth Riemannian manifold with bounded curvature, kappa's counting for that. And these sort of Hausdorff metrics are, sort of a couple different ways you could kind of do the zooming in. This winds up being kind of convenient for us to think about Hausdorff measures. So we think about the clusters sets as sort of having this low dimensional structure as articulated in this definition. And what we require from these cluster sets is that they don't touch. They cannot intersect. This is something we're working on relaxing, but right now they have to be non-intersecting. So we have sort of our like signal, right, which is these like low dimensional clusters, and then we have background noise. Okay, and the point we're going to make in our theorems is that we can have a lot of background noise for this. Okay, so I have sort of my cluster sets, and on the complement of that, the sort of diffuse background noise. So just as an illustration, again, no need for the clusters to be linear, but it's easy to draw a picture when they're linear. So here we have just like in 3 dimensions, we have one-dimensional clusters corresponding to these edges of this cube here. And then we have diffuse background noise sampled from the interior of the unit cube. So I do need to sort of introduce some notation to write down our theoretical results, right? So I need a total sample size, which is going to be the number of samples from each of the K clusters plus a background noise amount. And then I'm going to ultimately phrase my theorem in kind of like a signal to noise ratio. So I want to know how much am I sampling the smallest cluster or the most weakly sampled cluster. So my results will basically say something like, as long as n min is big enough relative to n tilde, then when we run spectral clustering with this longest like path distance, everything works beautifully. So it's a little bit technical, but that's a sort of, we need to introduce this. So something that we do to make it like work better in practice is like we denoise. Okay, so what we're going to do is compute nearest neighbors with respect to this longest leg path distance, and then say, okay, if your nearest neighbor distance to say your kth nearest neighbor, okay, this is a new parameter, is bigger than some threshold, we just throw away those connections. Okay, so this gives us a way of just saying like, okay, can we detect some of this like really diffuse background noise? And the answer is this is quite helpful. And our theoretical analysis will say exactly, what nearest neighbors you should look at and how much you should threshold. So just to sort of summarize the main results in this case, so if our noise level and tilde is not too big, that's this inequality here, and I'll interpret it in just a second, then if I run spectral clustering, right, if I build the weight matrix using the construction I described earlier, using this Gaussian kernel with the longest leg path distance, and I pick I do denoising by looking at like, the 10th nearest neighbor or something. It doesn't really matter if it's 10 or 100 is the point of this theorem. It just can't be too far out. And I'm sort of sampling the clusters roughly equally. Okay, then I pick my thresholding parameter in this range. I pick my scaling parameter in this range. Under those assumptions, two things. Point one, we correctly estimate the number of clusters with this eigengap. Point two, perfect accuracy when I run k-means on the eigenfunctions. So under these assumptions here, perfect results, or I guess everything we would want from this. So let me just try to argue that these are reasonable assumptions. Okay, so this condition here is basically saying how much noise can we take? And the point is we can take an exponential amount of noise. Exponential in what? Exponential in the smallest sample set, right? So n-min is like the most weakly I sample a cluster. And I get to sample it exponentially at an exponent that is the ratio of the ambient dimension to the intrinsic one. So when I have very low dimensional clusters in a very high dimensional space, capital D over little d plus 1 is really big. So in that case, I can take a ton of background noise. If, let's say, I'm in 100 dimensions and my clusters are like 99 dimensional, I don't get very much here. Okay, that's a hard problem for me. So this condition on n tilde is really like a signal to noise ratio. If the signal to noise ratio is high enough, then we can go for it. And so I wanted to argue that this is basically saying that this method is robust to the parameter choices, right? So the first condition is a condition on the denoising parameter, the second one on the scaling parameter in the kernel. And I want to argue these are big ranges, that like we're not trying to hit a bullseye with the parameters, that a lot of stuff is going to sit in here. So the point is that, again, when little d is small and capital D is big, the lower endpoint here is really close to 0. And the upper endpoint here is basically like order 1, essentially. So you have a very wide range of denoising parameters. And it's a similar story for the scaling parameter, albeit now the geometry of the clusters is the salient point, right? When delta, the separation between the clusters, is really big, this is easy to do. And so you can also see just from this theorem that if we try to bring these clusters to be really close together, eventually it fails, right? That we won't be able to see that there's a gap between them. We are working on ways of sort of allowing for the clusters to intersect, but this result requires separation. So I want to show just one example of like how we use this. So the idea here is I'm going to have my data come in, and this was an idea that my collaborator Anna Little had proposed a few years ago, and it is to say, okay, if I want to estimate the number of clusters with these spectral methods, then what we should do is allow the scaling parameter sigma to vary, right? So this is going to give us like a sequence of Laplacians or a sequence of weight matrices, and I'm going to look at how the spectrum changes as a function of that scaling parameter. Okay. And then I'm going to look at where there's a big gap in that plot, and that will simultaneously tell me the number of clusters, hopefully, and which our theorem says it should, and it will tell me a good choice of scaling parameter. So this sort of approach really lets us make the problem fully unsupervised. So just like a toy example, we took 16 of these COIL image data sets. So this is a kind of benchmark data set, and each object in the data set is a digital image of some household thing, like a rubber ducky or a cup or something. And so for each of these objects, there's like many pictures of it, and it's just pictures taken at different angles. Okay, so each class is maybe like 100 objects, roughly, maybe it's like 80, and it's just one object captured at multiple angles. Okay, so why might we think this fits our model? Well, yes, these are high dimensional things. If you think of the image as having dimensionality equal to the number of pixels, these are 32 by 32 images, so it's like 1024 dimensions. But like to generate the whole class, all I do is take a fixed template and hit it with rotations. So that sounds like an intrinsically low dimensional thing. I think trying to make that precise maybe a little bit harder, but motivation nonetheless. So what we did is we said, okay, let's build a family of longest leg path distance Laplacians with different sigma values and look at the eigenvalues. And that's the sort of multi-scale eigenplot we're seeing on the right. So each color is a single index of an eigenvalue, and I'm allowing the scaling parameter to vary. So blue here, the first eigenvalue is always 0. Doesn't matter what sigma is. So that's what this plot here is. This red one above it is the second eigenvalue, changing as a function of the scaling parameter. So for reasons that I think I won't get into, all of them are going to go to 0 as sigma goes to 0. All of them except the first are going to get very big as sigma goes to infinity. So we're looking kind of in the order 1 sweet spot between. And what we see is that here, there's a very large gap. Okay, I mean, I'm not going to look at the gap between the first and the second, but so there's always going to be large for large enough sigma. So other than that, where's a big gap? So there's a big one here, and notice it's fairly persistent with respect to sigma. Then there's also a big gap here, 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 and so on. And this is between the 16th and 17th eigenvalues, which would tell me, okay, for any sigma in this range, I can correctly estimate the number of clusters in the data. So that sort of validates, I guess, our sort of main theorem, but it does more, which is it says, okay, once I find one of the places where I have a big gap, let's just use that as sigma in our algorithm and then run spectral clustering on that, right? So I'm we've built up sort of a fully unsupervised framework, right? Data comes in, you compute, automatically, right? No human is needed to validate any of this. You compute the multiscale eigenplots, you look at where there's a big gap, that's going to tell you the number of clusters to run for k-means. And it's also going to tell you, or give you an estimate for a good choice of the scaling parameter sigma. So now I have all the stuff I need to run spectral clustering with this longest leg path metric. On this example, we get perfect accuracy. Basically, I think we had like 1 or 2 mistakes. The exciting thing for us was not getting high accuracy here, because if you run like Euclidean spectral clustering on this with like the right parameters, and knowing the number of clusters a priori, you can get like 90+% accuracy. This is not a hard problem in that regard. It's really the parameter selection and the automatic validation that we were sort of excited about. Okay, so something that Rongji brought up is like, how does this compare to more classical notions of shortest path, right? I mean, I was sort of saying this is highly density driven, right? It's like an L infinity geodesic. The classic shortest path that you would see in like an undergraduate computer science or discrete geometry class is like the L1 geodesic, right? So for that, I'm going to say optimize over all paths. And what's the functional on a path? It's going to just be the sum of the edges in it. So remember, the longest leg is the largest edge. So it's like L infinity norm of the step sizes versus L1 norm. Okay. What's stopping us from kind of interpolating between those? And the answer is nothing, right? I mean, we have to sort of it's very easy, I think, to design a family of metrics that's really going back and forth between, okay, when the sort of underlying parameters one way, you're picking up on this like geometric manifold learning properties of the data, right? Like the shortest path metric, which you can think of as kind of like, an interpolation of the geodesic in the continuum setting. And then as that parameter changes, you're moving towards our longest leg path distance. So we define with, this is with my collaborator Anna Little, but also with Daniel McKenzie at UCLA, we define these families of metrics that we're calling power-weighted shortest path metrics. Sometimes they're also called Fermat distances in the literature. So what it says is, okay, like let's minimize overall paths and let's do the LP norm of the step sizes. So in P is 1, right? This is just the sum of the edges. So it's like the classical shortest path. As P goes to infinity, you can see that the only thing that matters is like the longest edge. So this, generically, right, unless you have repeated edges of the same large size, this is going to converge as P goes to infinity to our longest like path metric. So what does this do? Like, why is this interesting? So what we find is that this P parameter really does interpolate between geometry and density. So when you have situations where, like, this is an ill-posed problem, I mean, unsupervised learning, I think it's generally kind of ill-posed without some strong assumptions. This P lets us kind of interpolate between different, possible clusterings in the data. So just like a sort of a simple working example, I'm showing you this kind of dumbbell data set that's common in the manifold learning literature. So you have, like, in one sense, like there's two clusters here, right? You should cut at the dumbbell and you'll end up with like a kind of coherent chunk here and a coherent chunk here, right? So this is what I think, people who like normalized cuts and kind of thinking about, okay, well, a good clustering should be one in which, you remove a small number of edges and then have like large, equally sized pieces left over. I mean, that's more or less what this partition corresponds to, this sort of just blue and red. One could also think in terms of density and say, well, I want to cut wherever there is like a topological gap between the clusters, if you like, right? Whenever there's like a cut through a region of low density. So what I've done here is I just said, okay, there's like a density gap here and a density gap here. So let's just cut in those places. And then you get this sort of 3 cluster partition here. One can also say, well, once I've done that density cut, this sort of half dumbbell should still be cut down the middle because that's very favorable geometrically. And what we can see is that as I change this P parameter, I basically pick up on each of these 3 clusters, right? So when P is close to 1, the sort of spectral clustering embedding gives me something where the right thing to do is to cut at the place that splits it geometrically. When P is really large, I get an embedding where the correct thing to do is to pay attention to geometry and cut into 3 pieces. And when I use something kind of in the middle, like P equals 2, I wind up cutting kind of I want to cut geometrically here, but then I also want to cut from a density standpoint here. So this is really kind of interpolating between the different interpretations of the cluster structure in this data. And so something we're kind of working on now is trying to take these power-weighted shortest path metrics and really think about what they're doing at the level of, like, okay, I have some manifold and some density sitting on it. If I get more and more samples and build these graph Laplacians using this power-weighted path metric, what is it converging to, right? Am I getting a continuum operator? How is it treating the density function? And we're this is something we're working on now, and I think it'll be kind of interesting and really give like a new model for unsupervised learning that I think kind of smoothly interpolates between, I guess, what I would call the 2 dominant mathematical schools, which are those in which you care a lot about geometry and those in which you care mainly about like the density patterns in the data. Okay, so I'm going to sort of switch gears and talk about sort of a different approach to these problems. Are there any questions? Okay. So as Ronji had mentioned, there's sort of an adversarial noise model here, which is one in which you have like high density paths connecting the clusters. And this is true for basically any kind of shortest path metric, right? Because it really says, I'm going to define the similarity between 2 points based on just a single path. Okay, ultimately, I only care about the best one. And so all it takes is, an adversary to put down one path that is potentially unfavorable to really mess up the meaningfulness of these sort of path-based approaches. So this is a kind of a classical observation that maybe one wants to do something a little bit robust. And we sort of learned this when we started looking at hyperspectral images, which are an example of sort of image, so the remote sensing images in our case, but each pixel is not a single, let's say RGB, triple, or even a single grayscale value, but it's a high dimensional vector where each entry of that vector is essentially capturing like reflectance at a certain electromagnetic range. And we were finding that these types of data sets were really not working well for these path metrics, that really we needed something much more robust for this. So what we wanted to look at was sort of data sets in which these observations are basically these high dimensional vectors. So I'm showing you for this sort of benchmark data set from Pavia, Italy, what like one data point looks like. So each of these colored plots here is one data point. Okay, they're colored based on their semantic label, right? One of these classes is like rooftops, one of them is like grass, one of them is trees. And our goal here is to, without seeing any colors, right, sort of group them into the natural regions. So just to sort of get a sense that these are like truly high dimensional images, I have basically the data set we're looking at. I'm looking at different slices of this high dimensional image. So this band 2 is like at a certain electromagnetic range, and you can see certain objects in this scene are really represented. If I go to a higher electromagnetic range, let's say by going to the 102nd band, you can see that other aspects of the image are emphasized. So, so these are very rich modalities, where a lot of information is captured in them, but that leads to high dimensional statistical problems, so potential challenges. So the approach we took here was to not really think so much in terms of path metrics, but to think rather in terms of like something like an average path metric. I wanted robustness to these sort of adversarial connections. And one way to do this is to think about random walks on these high dimensional images. So the approach we took is sort of falls under the genre of like kind of diffusion-based approaches or manifold learning approaches. So we build a weight matrix just with Euclidean distances on these high dimensional spectra. We normalize that weight matrix not to get a Laplacian, but to get a random walk operator. And then we use the time evolution of that random walk to find structures in the data. So this was an idea proposed by Koifman about maybe 15 years ago, which was to say, okay, build this diffusion operator P, and to compare 2 points, I'm going to let that diffusion run up to time t, and then each point has a transition profile of this operator, right? Like, what is the probability distribution for next steps at time t? And 2 data points will be considered similar if they have similar transition profiles. So the kind of interesting observation that we made was that, okay, as t goes to infinity under very mild assumptions, this operator converges to stationarity. Okay, that the diffusion kind of peters out, no more structures left to find, and you just end up at like your equilibrium distribution. So in that case, all the transition profiles are the same. So the diffusion distances are going to 0 as t goes to infinity. But for t that's not too big, not too small, you end up with a situation where you see convergence locally, right, to sort of what we call like mesoscopic equilibria, and not globally. And that kind of metascale convergence can be used to cluster. Right, so just from a practical standpoint, one can diagonalize this diffusion operator and get kind of a low dimensional coordinate embedding, similarly to spectral clustering. So how does this look for these hyperspectral images? So I'm showing you these are I'm taking these sort of high dimensional spectral images. They're like 102 dimensional. I'm just plotting them in the first, second, and third coordinates of the eigenfunctions of this operator. And the key point here is that they're pretty well separated, right? So I'm showing you the true colors, right? The ground truth labels instantiated on the embedding. But even without these labels, right? I mean, do you think you could, if I didn't show you the colors, come up with the correct assignments? I mean, I think some of them are easier than others, right? I mean, the blue and the yellow are really far apart. It would probably be easy to say these are their own clusters. You have a little bit of ambiguity with the 2 blues here, and then the green and the brown kind of flow into each other a little bit. So yeah, maybe you could do well with unsupervised learning in this case. So our algorithm was something that was a little bit different than spectral clustering because we wanted to do a couple of things. One, we wanted to be robust to clusters with small sizes. So this is typically a challenge for spectral clustering methods. And this was important for us because with these hyperspectral images, one often has classes that are quite small in terms of the number of pixels, that they're just rare things in these images. So we want to make sure we pick up on those. So the approach we take is we basically kind of find high density modes in the data, right? So these are going to be points that are high in, like, let's say, an empirical density, and then also are far in diffusion distance from other high density points. So we're basically doing a kind of like mode finding where we use the diffusion to sort of move quickly along high density regions. So we detect these modes, and then, to summarize, we basically take those modes. Each of the other data points gets sent to its nearest mode, kind of in an iterative fashion. It's a little more complicated than that, but I think that's sort of the way you can think about it. So we run this algorithm. It's fast, it's scalable, it's great. It needs to be for these big images, and we can get some pretty good labels. We call this learning by unsupervised nonlinear diffusion. So I'm showing you on the left the output of our algorithm. On the right is the ground truth labels. So we make some mistakes. I'm going to argue that if we forget mathematics and we just think as image processing people, we can correct some of these mistakes. But let me just say a little bit about, at a theoretical level, why this is a nice approach. It really comes down to this idea of finding mesoscopic equilibria in the diffusion process. So one way to kind of do this theoretically is to say, okay, as time is evolving, okay, I should be able to have it such that my diffusion distances make all points in the same cluster look close together, and points in other clusters still look far apart, right? So that's really what I want. I want this sort of maximal within cluster distance to be small, and the minimal between cluster distance to be very large. So if I can make that happen, lots of methods will work well here, including our LUND algorithm. But how do we make this work, right? I mean, the analysis that we have is basically to characterize the relaxation times and exit times of this Markov process. So we say, okay, depending on certain underlying geometric constraints on the clusters, like how elongated they are, how close they are to each other, if you run the diffusion process for a certain amount of time, right, you have to run it long enough so that you cohere within a cluster. So we have a lower bound on the time, but you don't want to run it too long so that you reach like a global equilibrium. So there's an upper bound on the time. So if you are in this temporal sweet spot, then your within cluster distances are uniformly small, your between cluster distances are uniformly large, bounded below. And these constants C1, C2, C3, C4, C5, these are essentially are explicit in terms of things like curvature, separation, and so on in the data. So just to give a picture for like why this is working, I think pictures like this appear in many papers on these diffusion methods, but we have our own. So what I'm showing you here is just some data where there's like multiscale cluster structure, highlighting the red dot here and showing you the diffusion distances from that red dot as time moves forward. So at the beginning, everything is kind of equally far. This is in log scale, right? So the -1 is like distance is 10 to the -1. So as t goes forward, first I look very close to all the things in my local cluster at one scale. Then I go to a higher scale, right? I let time run further. Now I'm close to all the things here. And then, eventually I run it to stationarity and I'm close to everything. So the bottom line is once I can control this sort of within cluster and between cluster distances, perfect accuracy comes out of it for free. I do have a condition that like if there's a very high density outlier, I have to watch out for that. But I think that was sort of a cost we were willing to pay to get better performance in practice. So let me just sort of argue that mathematics aside, one can improve this algorithm just with like a little image processing insight, which is to say, okay, these are the pixels, right? And I'm showing them in the embedded space, but what do they look like when I rearrange them back in the original image? So what I'm showing you here are my learned labels reconstitute as an image. And what we're seeing is that the mistake that's made, one of them is like over here, where I really have this sort of non-smoothness of the labels. And it's possible that the correct labels are really non-smooth. But a good prior to bring into these kinds of hyperspectral problems, especially when they're not in a city, is that the labels should be pretty smooth. Okay, so we can sort of instantiate that assumption and sort of allow the diffusion process to maybe be biased towards giving similar points the same label. So we have sort of a two-stage labeling process where as soon as we get into ambiguities in terms of like wanting to label things that are going to sort of give like highly speckled overall ground truth labelings, we're just going to not label those things. And then we do sort of like a kind of inpainting. So we do not do like Laplacian smoothing, but you could think it's like a similar family to that. So we end up with pictures that are a little bit more coherent in that case and give us some better accuracy. So yeah, I think I have like maybe 5 minutes left. So I'll just go say a couple of things about how to generalize this to semi-supervised learning. So what we were interested in was we were noticing we were making kind of catastrophic mistakes sometimes, that we were getting like whole clusters that were being incorrectly merged with another cluster. So, we were getting mistakes where, okay, if someone could tell me just no, don't merge those two things, we could get a lot better accuracy. So we wanted to design an active learning algorithm, meaning that, okay, I have a very small budget of labels, but I get to ask for the labels. So instead of getting like a random sample of labeled points, I can query the data and say, give me labels here, here, and here. So what we wanted to know is like, can we do this efficiently with our algorithm? So we did something that was a little bit, I think, unconventional in this literature. So the most common theoretical framework, at least for active learning, is to think like a supervised person and say, well, imagine I was doing like support vector machines. What I really want is labeled points that are going to help me set the boundary fast in the sort of high dimensional kernelized space. So I should figure out a way to how to estimate which points are close to the boundary. We decided to say, okay, well, we're doing unsupervised clustering. What we should do is find like a cluster-based approach to this. And all we do is we say, okay, now instead of identifying these modes and making them like cluster centers, just give me the labels for the modes, right? So these are in some sense like the most important points. And if I can get those right, they will sort of diffuse their correctness to the other unlabeled points. And this winds up giving sort of incredibly valuable performance improvements at very low cost, right? So I think I'm showing here the accuracy on a pretty, challenging data set, but, one can come up with examples where with just a couple of points, you go from like 70% accuracy to like 100%, right? I mean, you kind of need to fit this cluster model, but we find it to be super efficient and interpretable. Let me skip over this. So the thing I'll end on is, so everything here has been handcrafted, right? That we're really thinking about designing metrics for certain generative models. But I think that there is some benefit maybe to not doing that, right? I mean, it's a little bit hard to, I think, to do unsupervised deep learning because the kind of complexity of these deep networks makes it hard to figure out like what's a good generative model for clustering in this case. But what we can do, and this is some joint work with some people at Tufts and Harvard, is build deep networks that help solve hard signal processing problems that would be really good for clustering if we get them to run. So the approach we think about is like, okay, what I want to do is somehow like a dictionary-based learning for clustering. So I want to find, given this big, potentially nonlinear data set, I want to find a handful of representative exemplars such that if I reconstruct all my data points with these exemplars, I get low reconstruction loss, right? So given my observations Y, these are like my potentially high dimensional data points. I want to find a small number of atoms and corresponding coefficients so that if I reconstruct my data using this new representation, I have small error, right? But I also maybe want to impose some kind of regularity on this reconstruction that's going to be useful for clustering. So just as an example, right, what I'm showing here is like some data generated from like a noisy circle. So what the regularizer we were interested in is one that says, okay, I want to represent each data point well using the dictionary, but I also want to do it with nearby atoms. Okay, so I want to sort of think about doing like kind of almost like kind of sparse interpolations in this way. So the model we think about is what we call K-deep simplex. The deep is because of the algorithm we use to sort of actually solve this, right? So what we do is we say, given our data, learn me a set of exemplars A and corresponding coefficients so that I reconstruct. In this case, these are hard constraints, so I reconstruct perfectly. And I'm thinking about really doing like a convex combination of these atoms. So I have a simplex constraint, but the key insight is that it would be beneficial for me to represent my point yi, I should be using atoms that are close by to me, right? That I want to sort of have the spatial regularity imposed by the method. And what we find is that these give really good results for clustering if I cluster on the coefficients. Okay, so this somehow has like a feeling of like sparse subspace clustering, right? Sparse manifold clustering, where you try to find a representation for your data and then use those representation coefficients to cluster. So there's all kinds of beneficial denoising methods. It improves complexity considerably. The main challenge is solving this efficiently. And this is it's a dictionary learning problem. It's non-convex. In principle, not much you can do. And I'll just end by saying that what we really do is we build a sort of unrolled neural network to solve this efficiently. We find this is much, much faster than alternating direction of multipliers. And why do we like this theoretically? So this is something that my colleague on this project, Abby Tassisa, has proved, is that this gives you in some sense like a notion of sparsity in these settings, right? That I have this this thing I'm trying to minimize, which is like I want to use atoms to represent me if they are close to my data point. And what we see is that in practice, this means I represent my data point using a very small number of atoms, right? There's no benefit to reaching really far away, right? Because you get penalized so much in that in sort of the optimization function from going far away. So this can be made precise. You can guarantee sparsity of the representations under some kind of somewhat rigid assumptions. But in practice, we do see this kind of like geometric sparsity coming out of this model. And we find, it works pretty well in practice and it's fast. So just I'll end there. Just a couple things that we're working on. I mean, we're trying to figure out how to handle intersecting manifolds in good ways. And something we're really excited about that isn't really in this talk at all is moving towards like kind of more time series analysis and thinking about high dimensional chemistry systems, right? So the kind of high dimensional, very non-linearly correlated data sets that come out of molecular dynamics simulations and thinking about how to kind of quantize these things and develop reduced order models in that setting. And this is something that kind of intersects with this structured deep learning in the sense of trying to build structured deep learning algorithms that handle nonlinear spaces, in particular handle spaces of probability distributions endowed with Wasserstein metrics. So I will stop there, and thanks for your attention.
Thanks, James, for this very interesting talk. Any questions so far?